In this lesson, we want to look at something called the conjugate root theorem, and I've kind of cheated and gone ahead and written this out ahead of time. So let's look at what the conjugate root theorem says, and then look at a problem that we might see in this area. The conjugate root theorem says irrational and complex factors always occur in conjugate pairs. That means that if I've got an irrational factor, I have two irrational factors. If a 0 of my function is the square root of 3, then a 0 of my function is negative square root of 3. If a 0 of my function is the square root of 7, I also have a 0 of my function that's negative square root of 7. And consider what that means about your factors. If I have x plus the square root of 2, I have x minus the square root of 2. That also occurs for complex factors. And we've talked about that to some extent when we've said that imaginary factors always have imaginary friends. If I've got 3i as a 0 of a function, I also have negative 3i as a 0 of a function. So let's look at this in context and answer a question here. A quartic polynomial with rational coefficients has two roots of square root of 2 and 1 plus I. Find the polynomial. Well, if I know that the square root of 2 is one of the roots of my function, and I know that 1 plus I is one of the roots of my function, the other two roots for this quartic function, which should have 4 roots altogether, would have to be the conjugate of the square root of 2, which is negative square root of 2, and the conjugate of 1 plus I, which is 1 minus I. So I have found my other two roots. Well, what does that mean? That means I have zeros of, or x is equal to the square root of 2, x is equal to negative the square root of 2, x is equal to 1 plus I, and x is equal to 1 minus I. Well, those zeros of the function give me the factors of my polynomial. If square root of 2 is a 0 of my function, one of the factors is x minus the square root of 2. And if negative square root of 2 is a 0 of my function, my factor is x plus the square root of 2. I'm just moving it back to the other side of the equal sign. Now be careful with this one. I'm moving two numbers here. If 1 plus I is my 0, my factor is x minus 1 minus I. And if 1 minus I is my 0, then my factor is x minus 1 plus I. Now, I'm not going to do all of the multiplication here. You can do that yourself. But let me point out, if you're doing this kind of a problem, the first thing you need to multiply when you start doing things like FOILing are those conjugate pairs, because they're going to simplify tremendously, and you're going to make a lot of work. If the first thing I did here was x plus the square root of 2 times x minus 1 minus I get this big long string of numbers that I'm going to have to multiply. But if I multiply x minus the square root of 2 times x plus the square root of 2, when I multiply that together, I get x squared minus 2, a nice simple factor. And when I multiply x minus 1 minus I times x minus 1 plus I, if I do all the distribution there, I get x squared minus 2x plus 2. And then I'm going to have to do the distribution to multiply those together. The polynomial then turns out to be x to the 4th minus 2x cubed plus 2x squared plus 4x. I have, minus 4. And I've got 4 zeros of the polynomial, the zeros being square root of 2, negative square root of 2, 1 plus I, and 1 minus I. Think about it. How many x-intercepts do I have? These two are not real, therefore they do not give me an x-intercept. I only have 2 x-intercepts in this function, and those 2 x-intercepts are at the square root of 2 and negative square root of 2. All right, let's do another example of this same type of problem and answer the question, what is a polynomial, a third-degree polynomial function that has rational coefficients with roots negative 4 and 2i? So let me write that down so you have it to look at. What is a third degree? Okay, so think about that. What's that going to tell you about how many factors, how many zeros you've got? A third-degree polynomial function with rational coefficients. We're not going to deal with irrational coefficients at this point. That would be, did I have something that had a coefficient of square root of 3? And this doesn't apply to that. So I have all rational coefficients. And it has the roots -4 and 2i. Well, using the conjugate root theorem, we know that rational roots, irrational roots, and complex factors always occur in pair. Now, does that apply to rational roots? If I know that I've got -4 as a zero of a function, do I have +4? No. Remember, your conjugate root theorem only applies to irrational and complex zeros. But if I know that 2i is a root of this function, I know that -2i is a root of this function. So I need a third degree polynomial. 3 zeros. I've got all of my zeros. I'm not even looking for another factor for this. So my factors here are going to be x plus 4, x minus 2i, and x plus 2i. This is the fully factored form of this polynomial. Sometimes you'll ask for something to be fully factored. If it says fully factored, you need those imaginary factors. If I FOIL these, my imaginary terms cancel and I end up with x plus 4 times x squared plus 4. Now, this would technically be called factored over the reals, because all of those factors are real numbers there, x plus 4, x squared plus 4. And then if I FOIL that, I get my polynomial in standard form. X cubed plus 4x squared plus x plus 16 is the polynomial in standard form that has rational coefficients and roots of -4 and 2i. Notice it also has a root of -2i because those complex zeros, complex roots, complex solutions, complex factors only occur in conjugate pairs.